So, this is the final video for this, I think. In the previous video, I discussed the concept, I asked the question, what are perfect numbers actually communicating, right? What are they conveying? We were playing around with all these symbols and moving them around and doing different things and figuring out things, properties about them. As I like to say, there are these built-in properties to them that clearly define what they are and how they become created. And so we explored that. And what I was able to show was that we can actually communicate perfect numbers and what they're doing in graphical form rather than mathematical notation. So we conveyed perfect numbers through mathematical notation, and then we conveyed those same ideas through graphical forms, through a graph, right? And I called up the idea that what we're actually dealing with is spatial analysis and comparing spatial analysis with quantitative analysis, that is addition and subtraction. And so what I'd like to do here really quickly, this is the last video I want to do on this, and this one's the most all about just exploring ideas about how we could look for the search for odd perfect numbers. So we had this matrix, we have this formula. By the way, there are two things. I'm aware that formula that I figured out, came up with, is just a slight variation on the one that Euclid came up with. So it's not actually different. It's equivalent to, I just used it in a different way that I preferred, and that felt just more comfortable and natural given the matrix. Using it in the way that I was doing it with the matrix, it just felt natural to keep that formula, and felt simpler actually in that way. And the search for, you're right. So then the idea that I want to explore here, and this is really a video mostly for mathematicians or anyone that wants to explore this further, because arguably, if you are a mathematician, you probably know more about matrices than me. It's highly likely. So what I hope is that the idea of the matrix, the perspective of looking at it and being able to see that property of inverse symmetry can maybe lead us to down a path that either shows that yes, to a proof for odd perfect numbers, or something that refutes, right, the idea that odd perfect numbers exist. So I just want to talk about that really quickly, right? The ideas of the matrix, we think would look something like, right? We've looked at the number 2 as the base prime. So this could be any base prime, but I do think it's important that it's got to be prime here. So it'd be 3. We want to start looking at 3, 5, right? And so times 3, x times 4, x to the power of 5, and x to the power of n. And this side is going to be, theoretically, x to the power of n plus 1. Now this is where it gets interesting. Minus 1, maybe there's another number that we could subtract to generate a prime, right? So let's say we use 3 as our base. There's a lot to explore here. I think actually minus, so let's leave that as minus A. Let's not define that as 1. That's an assumption that 1 is the only way to generate a perfect number. But maybe if we use 3, we could see, right? But, so what should we look for? We need to look for prime I don't know, yeah. I'm just gonna say, I'm gonna generalize matrices with inverse symmetry. It's the end of the night and I'm tired, clearly. And, right, so once we get to this state, it should work its way back up, right? So there should be this down, this up, and maybe there's multiple lines of matrices, right? Like it might not be 2. Maybe it's 2 for the prime number 2 as the starting base, right? Prime. Maybe there's 3 rows. Maybe there's an infinite number of rows of matrices that somehow have some kind of symmetry to them. I don't know. But again, going back to the idea of what is this actually showing in a very generic form, and I'm going to do dot, 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 is changing a shape while maintaining area. It's really important to remember. I think inverse symmetry is one of the properties, the first principles of perfect numbers. One of the key ingredients, if you will. My gut tells me, but we can find a lot of inverse symmetry, so it feels like there should be more than just these perfect numbers. We are changing a shape while maintaining area, right? So just a reminder, we had, let's go to, let's go to, I'm gonna do something like number that's perfect, 2, which is 28. Had the factors of 1, 2, 7, 4, 14, which could be expressed as a matrix in matrix form as or 1 plus 2, 4, and 14, 7, right? Just like that, right? And then we also, for odds, these must sum must be even, right? Because we definitely have this 1 over here, plus 1, which is a factor of every number. So we cannot get rid of that 1, all right? Actually, I'm going to show something here really quickly too. There's one other way to write this. I don't know if this is helpful or not, or we could do something kind of fun. And that is 2, right? 28. 2, 1, 14. 2, 2, 7. So this kind of cleans it up and gets the 1 inside the matrix. Now obviously, so then what you have to remember though is that there's this, right? 2 to the 1, 2 to the 0 is 1, so 1 times 28 is 28. 2 to the 1 is 2, 2 times 14, 28, and 2 to the power of 2 is 4, times 7 is 28, right? So, just an FYI, I wrote it out like this because I wanted to focus in on the fact that each line was actually the product that we wanted. This one, I felt like it confused it, and so I decided to keep the 1 out of the matrix and just focus in on because the symmetry is actually still there, interestingly enough, and maybe that also is another hint for the more generic one as well, right? But maybe there should be, well, in this one I added the 1 outside, but right, you could, x to the 0, right, correlates to the answer, right? So this is our product. The sum of all of these is our, but, so there's that theory, that idea, possibly, right? And then I wanted to just reiterate, I suppose, is that if we look at this, if we use this as our example, and in graphical form, and what are we doing, right? Again, what are we doing? We are changing a shape while maintaining area. Right, so let's do this real quick, hopefully. All right, so we have 2, something like this, 2, 2, 6. So we have this shape right here, right? This is our first one, 2 times 14, so the area is going to be 28, and that's equivalent to doubling our first factor, 4, and having our second one, so 2, 4, 6, so then we get 2r prime. But area of rectangle. Oh, I'm tired. Area of rectangle is equivalent equivalent to sum of all factors excluding the area, right? So that's what we're actually seeing here, area of rectangle. So one rectangle is equivalent to taking this line plus this line plus this line plus this line. And when we add those up, what we get is actually equal lines, right? There's that symmetry portion. This line, the addition of what do we get? No, they're not equivalent lines, right? Because 2 plus 14 is 16. 4 plus 7 is 11. So they're not equal lines, but we do have a line that's, let's do 2 plus 14, 2 plus 14, plus 4 plus 7, right? Plus 1. 14 plus 6, 20, 27, 28. This length is 28. Length of all the pieces is equivalent to 4 times 7. Or area. Right? And then again, what do we have here? Reminder that length we're dealing with, so we're comparing. So we are comparing length to area. In other words, i.e., quantitative analysis, that is to say, comparing quantitative analysis with spatial. Or right? This is a critical factor to remember. We can visualize it this way, line up all the factors. That should be that. And final thing to remember, quantitative analysis is slow. Spatial analysis is fast. Addition is slow. Spatial analysis, i.e. multiplication to addition, is fast. So that is why we need to consider ratios. Because if the multiplication goes too fast, there's no way the linear is ever going to keep up. So there's this, seems to be this ratio, right, as I mentioned before, where we see that the ratio between 2 to 3 is 0.6 infinitely, right? And then every single other perfect number, the ratio of the last two lines starts to tend towards 0.5, but will never hit 0.5, right? It'll seem like it's 0.5. It'll seem like it's almost half, right? So something else to consider as we look the search, right? And I just saw the video yesterday. I'm making these today. I have done absolutely zero research into it or experiments into it. And then obviously the lower prime numbers we have to start with first. Start with 3. Because these grow exponentially quickly, right? These numbers go from 6, 28, 496, 8191, 8192, I can't remember. And then, right, and then you start at 33 million, right, or whatever it is, right? So it's the rate of growth is absolutely massive for these numbers, for these searches. So the lower we can keep our search, the better, right? So right? Right, so there we have it. I think, all in all, I hope, maybe, someone much smarter than me can see this and go, I know what to do, right? All we have to do is take this matrix, plop in this, here's our symmetry, and we were able to show that, yeah, the next prime 3 in this sequence, right? I'm excited about this thought though, that A might not need to be 1. I forgot about that. I hadn't thought about that. So maybe there's another number that this could be, but it would have to be odd, I think, right? Because then we gotta correlate it to that one, right? Which throws everything off. If this is even, this has gotta be odd. So it'd have to be 1 or 3. I don't know. I haven't played around with it, right? So, but I think these are actually the core properties that need to be considered when pursuing odd perfect numbers. All the other patterns that like Veritasium showed are neat, but don't help us in understanding the properties, whereas these are actually the properties that we need to be aware of, right? And there's this flow. We can flow it, all right? So, all right, that's it for me. I'll be working on posting these up. Hope this was interesting to someone. It's very interesting to me and very fun. Thank you, Veritasium, for posting the video. This is cool. I'm wondering if anyone can use what I've stated here. I'm hoping that someone can use what I've done here to crack this problem and finally get some kind of resolution. Again, with using a matrix, possibly. All right, that's it. Thanks.